Good day! I'm Dr. T and welcome to my office. So today I would like to talk about light. Now, I need to be a little bit upfront with you on light. I'm going to be hand-waving over a few things because there's a bit of a rabbit hole, and I'm going to mean that meaning in more than one sense of that metaphor. See, about 150 years ago, light broke physics. It's like, how do you break physics? Well, if you go back further, say the time of Sir Isaac Newton, one of his big things that Sir Isaac Newton did, and the reason why we call him Sir Isaac Newton, is that he worked out an entire field called optics. And this is the field of bending light to get it to do what you want it to do and working out the math, etc. The field of optics treats light as if it's a wave. So we assume that light is a wave, it's coming from your light source, it's potentially a whole blend of different waves, and as it's traveling through things, those waves will behave like any other wave, like those in the ocean or that of sound. So in this idea, we've got light as a wave, it's traveling through air or glass or whatever, and we can do some really interesting things with it. We can separate them out into different wavelengths, which, since they would be going the same speed, would also be different frequencies. Now in sound, you think of frequencies slash wavelengths as tones. In light, we see those as colors. Although it's wrong to say that a certain frequency of light is a certain color, since color is a very subjective individual thing. If you look at different cultures, they will have different numbers of colors. What one culture might call blue and another culture might call green, in a different culture, which I think I've got 3 cultures here, but you get the idea. One culture would have blue and green. Another culture might just call, say, grue. And that could be, you know, light green and light blue as one color. So, yeah, the idea of color is a lot more subjective and a lot more talking about how we as humans think about things than what's actually going on in the underlying physics. Now, with the underlying physics, though, you've got different wavelengths, and those are what we're going to perceive as color, assuming they're ones that our eyes can actually detect. There's a whole lot of different wavelengths that you can have, and corresponding frequencies. So you can have wavelengths that are absolutely tiny, much, much smaller than atoms. Likewise, you can have wavelengths that are the size of cities. And this is going to make up an entire spectrum. And yeah, that's what we call it. We call this a spectrum. The visible light, the ones that our eyes are capable of seeing, is actually a very tiny portion of the spectrum. Now, when you've got this, you've got your wavelength slash frequency, and remember, assuming the speed is fixed, those two are locked together. Now, light can change speeds. It does some really interesting things when it enters materials. Light is what we call electromagnetic radiation. Radiation is simply energy being emitted from afar. This could be coming off in the form of light, something that's on the electromagnetic spectrum, or it could be particles flying around. It gets a little bit of a bad rap. That's really what we call ionizing radiation. That's the stuff that can do damage by breaking atoms and molecules. Whereas just kind of radiation in general, some of that might be able to do it, but you've got visible light, which unless it's really, really bright, like on the back end of a laser, it's not going to do much. Now, obviously, enough of anything, like a good old laser, you can use that to cut with, etc. So you have to respect it. This is electromagnetic radiation because it's got, electrical and magnetic property. And that's kind of like saying a dollar bill has a currency property. It's not really a property, it is what it is kind of scenario. These are a wave in the electrical and magnetic fields. Because of this, it's able to interact with things that have electrical and or magnetic properties to them, like electrons. And this is how it's going to be interacting with your eyes by having different atoms in your rods and cones that have electrons that are particularly sensitive to interacting with light of certain wavelengths. And thus, then your brain stitches that into what we consider color. Now, how did light break physics? Well, that actually goes into the way your brain stitches together color and a couple other weird properties. See, when you're dealing with electrons and light, the way the electrons are interacting with that is by responding to certain packets of energy. And so you think, okay, the more energy I have, I simply crank up the intensity of the light. I make it brighter. If it's a wave, I would make the amplitude more. However, the electrons don't really interact like that. That is important for them, but it's also, they're really interacting with kind of this frequency slash wavelength. It's as if light is coming in little tiny packets, what we now call a photon, and that it's quantized. And that's where we get the word quantum physics. We've got little quantums of energy buzzing around. This was confusing because now light is behaving like a wave and it is behaving like a particle. You know, if you think ball bearings or, sand, things can travel like those. And it's like, what is this? It can't be both, can it? One of the experiments that really broke physics was the Michelson-Morley interferometer. In this particular experiment, they were testing what must be the case if light is a wave. All waves travel through things. Sound waves travel through air, ocean waves travel through oceans, the wave travels through fans at a stadium, all waves travel through things. Therefore, light must be traveling through something. And the hypothesis had been there was a very viscous, very dense fluid surrounding everything known as the luminescent ether. And so they were going to detect Earth's motion through it by shining light in two different directions, measuring its speed, and detecting which one was going faster because the Earth was going through the luminescent ether. And they both came back at the exact same speed. Okay. Let's try this again. This can't be right. We've just disproved that there's a luminescent ether, but there has to be, because light is a wave. The only way it couldn't be, or only we could have a true vacuum, no luminescent ether, is if light was a particle. And you know what? Light as a particle actually makes some sense elsewhere. That's why light would cast shadows. Shadows are things you see of particles. Imagine if you were to, say, accidentally stand in front of someone spray painting. You get paint all over you, and then whatever they were trying to spray paint would have a U-shaped gap of spray paint. Well, yeah, that's a shadow. This is a bit of a problem, and this is what I meant by light broke physics about 150 years ago. A gentleman by the name of Einstein, Albert to be precise, comes up in 1905 with the solution. And this one is trippy. It's both. Light is both a wave and a particle. It is what we call a photon. By being both a wave and a particle, it's able to do all kinds of weird trippy things that otherwise it wouldn't do, and it seems to be, very convincingly, that it, yes, really is both a wave and a particle at the same time, which is weird, to say the least. But with that said, we're mostly going to be focusing on light as a wave because optics and most of the emphasis on understanding how light works typically is best explained as a wave, but sometimes we're going to have to think of light as a particle, such as how it actually interacts with your eyes. Because for the particles, for your eyes to detect them, it's going to have to be able to absorb a single photon or several photons. Your eyes don't trigger on a single photon. And in order to do that, those photons need to interact with electrons in the retinol within your rods and cones. And the only way they can do that is if they have the right amount of energy for that tiny little packet of light. Okay, this is getting interesting. Now you might ask, well, where does that energy come from? What determines the energy? And that is the frequency. The frequency of light determines the energy per individual photon. The intensity of light determines how many photons you get. Thus, your eyes are doing two things. One, they're measuring, okay, am I accepting a photon or several photons of an energy that this particular cell is able to see? Say it's a green cone, and therefore they would have energy corresponding to greenish light. Well, in that case, yay! How many of them am I seeing? The more I see, the more I tell the brain, hey, I saw another one. And thus we see the intensity of the light and look at its frequency, the color of the light. Of course, once again, frequency and color are very interconnected things, but color is much more a psychological and sociological thing than frequency is. So frequency is the base, color is what we add on to it. In later videos, I'll jump into things like optics and other cool things with light. Until then, see you next time.